All right, welcome to video 10, part 2 for applications of the first derivative. What we're going to start looking at now after talking about in part 1 with increasing and decreasing and how the derivative helps tell me that, we're going to start looking at now what's called relative extrema. Now, this is a terminology that you should have heard in pre-cal, at least in terms of extreme values. We're going to kind of review some of that here, which you'll see on the screen. What I'm talking about when I say extrema is I'm referring to extreme values. And so you can kind of see how the terminology is really, really similar. Probably the most difficult part is just the proper way of speaking. If you want to talk about plural for extreme, that is called extrema. And so you'll see that when I talk about maxima or minima, or when you're reading through math books, if you're looking at plural for max and min, it's actually not correct to say maximums and minimums. You would actually say maxima and minima. And so you'll see that written out a little bit more when we get into part 3. Okay, so in part 2, we're going to look at what does it mean to be a relative extrema and what does it mean to be absolute, essentially. So again, what we're looking for are the extreme values of a graph. And when you think about the word extreme, you pretty much think about extremes in terms of really, really hot temperatures or extremely cold. We're talking about really, really high points and really, really low points in any kind of context. And so in general, that means we're looking at maximum and we're looking at minima, right, and maxima. And so there's two types specifically. Now we're going to focus on what's called relative, but I do still want to illustrate both of these cases here, so you go ahead and get introduced to them now. Those two types are global or absolute extrema, and then local or relative, which is the title for this part, extrema. Now global, if you were to think what the word global actually means, you would imagine globe, world. We're talking about out of the entirety of our world, what is the highest and lowest value. So if you were to look at the entire Earth, there is an absolute highest point on this planet. If you were to look on this Earth, there would be an absolute lowest point on this planet. And so we would call those absolutes or global extrema. When I talk about local, we're talking about neighborhoods. All right, so we're talking about a very, very specific region. We're zooming into a graph and looking and just saying, okay, well, relative to the world around us, like our own little world, what are the highest and lowest points? So relative extrema don't have to be specifically the highest points overall. They can just be any high point. And so we're going to go through and kind of define that a little bit more specifically. We will look at absolutes a little bit later. Our focus right now is really just kind of defining in this kind of realm. And so I've got an example to kind of look at here and really just kind of practice this view of what does it mean to be a global versus relative? What does it mean versus absolute versus local? In this kind of part, you'll see I've got a curve here in blue. So here's my function. And I've labeled out some very specific points, A, B, C, and D. I'm not including the endpoint here since it doesn't continue. We don't know if the graph is going to curve back down or keep going up, so I can't talk about that one. So the endpoints are never necessarily going to be included here. I'm really only going to focus on these specific points here. And so if you look at this graph as a whole, where would you say the global maximum would be? Well, hopefully what you're looking at is you're saying, okay, what's the absolute highest point on this graph? So that would happen at C. So the global max would be at C. Where would the global min be? Well, we got B. So, all right, well, what about relative and max and relative min? So this means if you were just to focus on one portion of the graph, what would a highest point be? Well, one answer for relative max would be at the point of A, because, and I'll see if this works on here, I didn't try it first, but if I was to zoom in just here at A and I disregarded everywhere else on this graph, notice how this would be a maximum at this point. We know it's not the highest point overall, but it is the highest point in this neighborhood. So that means A is called a relative max, and so I include that here as part of my answer. Now, notice though, C would still be a relative max here because C is still the highest point relative to its own neighborhood or relative to the neighborhood of the entire graph. And so there are two relative maxes here. Relative mins would therefore be D, and B, because those are the lowest points in their respective neighborhoods. And so one technique mathematically to do, and this will be touched upon in the next set of kind of formal definitions, is that essentially what you do is you actually create these little neighborhoods around these points here, and we call them a, lowercase b. We choose this neighborhood here, we choose this neighborhood here. You take little cross sections and we say, okay, in that cross section, then this is the lowest point or this is the highest point, and that's how we define max and mins. Something else I want to point out before we kind of move on is notice that when we deal with relatives, relatives are just any mountaintop or any valley, so they can include globals, right? It's just any highest point, any lowest point. And so there can be multiple answers for that. But in terms of global, there can only be one set of global maxes, or there can only be one set of global mins. In other words, generally there's only one of each. Now, if a graph came up, so let's just say this graph did continue, and we hit the same height as C, and we called this, say, E, then this graph would have two global maxes because they would hit at the exact same maximum point. Y value their output. So it is possible to have two global maxes, but we're mostly not going to see that. We're mostly just going to see one or the other and try to keep things somewhat simple. All right, so I've got the kind of what we just talked about in words I have written out. So you have your relative max and your relative min. A function f has a relative maximum at x is equal to c. If there exists an open interval a to b containing that c, such that the function is always going to be less than or equal to that value for all x in that interval. So again, what this is talking about in a lot of math words is if we were to pick a little neighborhood, like a local interval for a to b, then a y value at a specific point is the highest point out of that entire interval. So if I was to sketch again just a brief, this is kind of what that little neighborhood for A looked like. I could essentially say, here's my A, here's my lowercase b. This would be my point for C. C is inside this interval. And if I was to pick any other x value here and go to their y values, they are all less than or equal to this highest point. So I can say that this would be a relative maximum. And so therefore, in contrast, or if you were to not necessarily contradict, but negate some of these terminologies, you would have the definition for a relative minimum, right? A function f has a relative minimum at x is equal to c, so at a specific value, if there exists on an open interval such that that y value at c is less than or equal to any x in that said interval, then by definition we would have a relative minimum. All right, and so this works again very, very similarly to the top. If we were to sketch something that we knew had a minimum. And so I could say, here's my a, lowercase a, here's my lowercase b. If I was to pick this value c here, which is in this interval, notice that its y value is less than or equal to every other y value in this interval. So that means at c I have a relative minimum. All right, now before we get into kind of the rest of the examples and really kind of defining now how we can find these relative maxes and mins, I want to kind of just review with you something that you may not have seen before, but something that's taught and that I've taught a lot in my on-level calc classes in previous years, which is looking at the building blocks for curves. In other words, every curve can be essentially broken down into 4 individual puzzle pieces that are then scaled to any size that you need them to be. And the way that these are essentially sketched are based off of these 2 ideas, whether I'm increasing or decreasing in the curvature, so the bend of the graph. If you want to think about a bow in terms of like a bow, like bow and arrows, how is the bend? Is it bending out or is it bending in? Because let's say A, for example, the first type of building block, let's say I want to be increasing. Well, there's 2 ways to be increasing. So I'm going to put these kind of above one another. One way is to increase, but bend out. And out, I mean, just in terms of up. And so my graph could do something like this. Well, I could also increase by bending in or bending down. like this. So there's two ways to sketch here. The other way is to draw a straight line. We're looking at curves specifically, some things that are a little bit more important, or at least more unique. All right, and then in B and D, there are two ways for a graph to decrease. The graph can decrease and bend out, so it would look something like this, or it could decrease by bending in like this. And so you could take essentially each one of these curves, and by putting them together, we could essentially create any kind of graph, any kind of function model that you would like. So what I'm going to do is actually do this. So we've got 4 different options. I'm going to walk through and we're going to pair up, and we're actually going to come up with every single pairing as we go through and kind of investigate what happens at the points where these two things would meet. And so when we do this, let's take a look at the first one. You can kind of see the couple ones right here. All right, so the first thing I did is I took A and then I matched it with C, or B, I think. Go back up, make sure I did my labeling right. Yeah. So I took A and I matched it with B. So you can kind of see in terms of my curvature here, there's my increasing but bending out. Here's my decreasing and bending out. So putting those together, notice it looks like a parabola essentially facing down. And what I want to do is I'm going to go through and we're going to answer the same questions every single time. And my overarching idea here is to think about what's happening in each different scenario. And we're going to try and come up with some guidelines for when curves have a max and when curves have a min specifically. And so here at A, so this single x value right here, would this be a maximum or minimum for this first example? Well, this first example, hopefully you're looking at, and you could register that this is a maximum, right? This is a peak. It is the highest y value out of every other y value in this piece here. Well, what about where is this function increasing? All right, well, this function is increasing to the left of A. And so we talked about in part 1 that if I'm increasing, then what we're really looking at here is where is the derivative going to be greater than 0? And we know that this is going to happen when my x's are to the left of A, so when x is less than A. Well, what about where is f decreasing? Well, we know that f is going to decrease when the derivative is less than 0, so when the derivative is negative. And from the graph, we know that this is going to occur everywhere to the right of A, aka where x is greater than A. So notice essentially we have this change here. We have f prime going from positive to negative at this location as we read it from left to right. And so because of that, notice what would the actual derivative of f at A be? So if you were to derive f and plug in this value for A, what would you get? Well, remember the derivative represents its rate of change, or the slope of the tangent line at this point. So if I was to sketch that, because this is the maximum and this is the peak, this means that the derivative at A is going to be equal to 0 because there's no more change once you get to the highest peak, right? You increase, you increase, you increase. But when you reach the peak of something, you stop because I can't go up anymore, right? There's no more change. The only thing I can do is the next step is to start going down. So at that moment, at that instant, there is no change. Therefore, its derivative would be 0 and its tangent line would be viewed as horizontal. So a horizontal line has a 0 slope. And so again, I get that the derivative is equal to 0 here. So in conclusion, for this first part, notice just a couple points that we have. In this kind of example, we have a maximum. With this maximum, we go from positive and then into negative because I'm going from left to right. And then specifically at this maximum, its derivative is equal to 0. All right, well, let's take a look when we're looking at the counter to this. So essentially, if I was to take those building blocks and specifically put together C and specifically put together D. So what if I did the decreasing bending in and the increasing bending in, and I put them together in this way? And so I think this is D, sorry, and this is C. Oh, well, would I have a max or a min here at A? Oh, here I have a minimum. It's the lowest point on this curve and in this little interval that I've got sketched out. Well, where is f increasing? Well, hopefully you're answering based off of our left one. So we know that f prime is positive when x is to the right of a this time. So as you go past a, so any x value greater than a, this graph is going up. So its derivative is positive. Well, what about decreasing? Well, f prime is negative when I'm decreasing. And this is occurring specifically when x is to the left of a. So at any value to the left of this a here, this vertical, my graph is going to fall. Therefore, the derivative for any x there is going to be negative. Well, what is f prime of a at a? Well, just like last time, if we were to represent this and draw a tangent line here, notice that that tangent line would be horizontal. Well, what's the slope of a horizontal line? Well, the slope there is 0, so that means the derivative has to be 0. And again, the reasoning is because it has a horizontal tangent line. And again, if we think about this in terms of like walking into a valley, or if you're walking down a hill, at some point you're going to reach the bottom of the hill, so you can't walk down anymore. You've reached the pinnacle at the bottom here, and I guess pinnacle is not the right word, but you've reached the ultimate lowest point where I can't go down anymore. The next step you have to take will take you up, and then up, and then up, and then up. So you have this decreasing change, 0, and then increasing change as we go. And so this is how this answers. So I'm going to put these two up. Take a look at these two, and I want you to try to fill these out. I'm going to pause for a second, pause the video if you need to, and then I'll go through and kind of work these out. These are two kind of weird examples. You'll notice this is essentially taking an increasing graph that bends in, so this would be C, for example, and then it is pairing it up with a decreasing bending in. So it's essentially the reverse of the one that we looked at before, so C and D. What if we put them together in the opposite order? Then what would we get? And so it actually creates this kind of graph right here. And then the fourth part here, it's the same as the first example, but we swapped them. So now we're doing B and then A and putting them together and looking at what happens. All right, so what would I have here then at A if I was to look right here at this point where these two things would meet? Well, hopefully in terms of maxes or mins, you can look at this and say, although it's weird, this is still a maximum, right? This is the highest value here out of this entire section of the graph, so it would be a relative max. But what about where is f increasing here? AKA, where is f prime positive? Well, if you're looking at this and reading this from left to right, we could say that this is positive when x is, to the left of a. So when x is less than a. Where's this graph decreasing? Well, it's decreasing when the derivative is negative, and this occurs when x is to the right of a. And so we can, again, double check that from left to right. I'm increasing to the left, decreasing to the right, and there are my inequalities to match that. Well, here's kind of the tricky part, and this is something that we haven't seen a ton of. What is the derivative at a here? In other words, what does the tangent line look like? Well, recall again, the tangent line is just an extension of the curve at a point. It represents how the curve is changing at that moment. Well, if you were to look at these changes, so this line would look something like that, and this one would go like that, and this one would go like that. Well, at this corner, the tangent line would be going perfectly up. Imagine this was like a roller coaster and you were sitting in a chair here, which direction you would be facing. Well, you'd be looking straight up into the air, and it matches again if you're coming back down. So notice it's kind of like you're going up. I'm going up along this line here at this point, and then I'm following it back down. So the tangent line is vertical. Well, what's the slope of a vertical line? Well, a vertical line has a slope that is undefined. It does not exist. And that's because I have all of this rise, but there's no run. So if I'm thinking about slope in terms of rise over run, I would get some kind of number up top, but it would be 0 on the bottom because I'm not moving right or left anymore. And this is undefined. I can't divide by 0. And so this happens again whenever you have a vertical tangent line. And this is an example in a graph when this would happen. So when you see a point like this in a graph where your curve comes together and it's kind of hidden by this point right here, where the curve comes together at this point like this is what's going to happen. We still have a maximum there, but the derivative does not exist at that value. Just to plug in a word there, we say that f is not differentiable at a, meaning if you were to derive it and try to plug in a, you wouldn't get an answer. All right, but what about the fourth example here? When we pitch together b and a in that order, would I have a max or a min at a? Well, in this kind of scenario, I'm going to have a minimum, right? It's the lowest point relative to the rest of the curve. All right, what about where is f increasing and where is f decreasing? Well, f is increasing. This again means that f prime is greater than 0 when x is greater than a, right? Everywhere to the left of this point here, I'm going up. And I'm decreasing, so f prime is negative when x is to the left or less than a. And so I can see that everywhere over here, my graph would go down until I get to that point. Well, what about the derivative at a? Well, if the third part made somewhat sense and you could take an educated guess, hopefully you're saying that the derivative here is d and e, because this is just a flip of before. This is going to be a vertical tangent line at a for this curve. Again, if I was to draw the tangent line here at this value, this tangent line would be going straight vertical. And I think visually this kind of helps again when I follow the curve, because I'm going straight down and then I'm starting to go up at that exact moment. And vertical lines have a undefined slope, therefore its derivative would not exist. And so I have this. And so let's just kind of review a little bit what we've got. Okay, so let's specifically look at when we had maximums and what we found in terms of our information, like what they had in common. So we had a maximums in the first and third example. All right, and so when I had a max here, notice that the first derivative going from left to right, it was positive to the left and then negative to the right, and my derivative was equal to 0. All right, for the other maximum, notice here I was positive to the left and I was negative to the right. Interesting. But this was D and E. All right, well, what about my minimums? For my minimum, we had a difference here because now I was increasing to the right and decreasing to the left. So it went from down to up, which makes sense because it's a minimum. And this happened in the fourth example again, when I had another minimum, where I was going down and then up. So it's a little bit different from maxes. But one thing that was very, very similar was that for this minimum, f prime was equal to 0. And for this derivative, it was d and e. And that's what I really want to focus on. That for my maximum and minimum, we found that the derivative at that value was either equal to 0 or f prime of that value did not exist. So in other words, does this give me a good enough outcome to guarantee that I'm going to have a max or a min, right? Does this give me a way to find them? And the answer to that question is no. And I want to show you that by showing you 4 other different kind of combinations here for these graphs. So we looked at, again, just really 4 different pairings of these. Well, let's go through and set up another set of pairings here because there's one more condition that's really, really important. All right, so let's go through and look at these next ones. So you'll notice these 2 graphs that we're going to first start out with for F here are 2 graphs that should look familiar. Like this one is essentially a cubic when you look at the first one here. And notice that I'm essentially creating it by using the pieces of A and using the piece of increasing. So this is C, sorry. So it's the 2 increasing portions of the graphs, one bending out, one bending in to create this cubic here. And so at A, at this point here that I've got marked off, the point where these 2 things would meet, do I have a max or a min here? Well, hopefully you're saying that it's neither, right? There's nothing, because this graph is increasing, so it looks like it's going to be a max, but then the graph starts going up again. So this point isn't the highest point in any kind of neighborhood that you could draw, because there's always a coordinate on the right-hand side that's going to be higher. And it's the same thing in terms of a min. Although this point right here is lower than all of these, it's not lower than any of these. So it's neither a max nor a min here. All right, well, let's go through and kind of finish out. So where is this function increasing? So we know that the derivative is going to be greater than 0 when I'm increasing. Well, in this scenario, notice I'm increasing to the left of A. but I'm also increasing to the right of A. So I'm actually increasing when X is just not equal to A. It's everywhere but A. So where is this function decreasing? Never. This function is never going down when you read this from the left to right. But here's kind of the next question. What about the derivative at A? So in other words, if you were to draw the tangent line here, well, if you think about how you're traveling here from the left, when you hit this point right here, you're essentially going almost horizontal. And that's actually true. The tangent line at this point is actually horizontal. So the derivative, which would represent its slope, is actually 0. But notice again, this was not a max or a min, so just this isn't enough. All right, well, what about in this next part? So if we took just the decreasing parts, and I specifically took the decreasing parts, I think this is D, and this is, what part is that, B? So if I took the pieces from earlier, D and B, and put them together, essentially it's a cubic that's been flipped. Like we talked about earlier, this is neither a max nor a min. It's not the highest or lowest point. Well, is this function increasing at all? Nope. But it is decreasing. And just like the other one, it's decreasing everywhere but at this specific value at A. Because at this moment, I'm sitting still. So I would say that f prime is negative everywhere but A. So what's happening at A? Well, it's a horizontal line. F prime of A is equal to 0. Right, this cubic, if you were to imagine drawing this, when you sketch it, your pencil will go flat for the briefest of moments, and that briefest of moments is enough to get this result. But again, just because the derivative is equal to 0 at this point doesn't mean I have a max or a min, right? Just because the derivative is equal to 0 doesn't mean I have a max or a min. All right, let's take a look at the final two setups, and these are kind of weird. I think they look like seagulls that you would draw if you're trying to like sketch a beach. And so this is essentially taking these same pieces and putting them together. So if I took two curved out pieces and put them together, what would this look like? And so in this case, let's say this is the bend out and increasing. So I think this is A and A in terms of combinations. Well, at this point right here at A, this is neither a max nor a min. So this is neither again. Same situation as before. This point is higher than every point here, but it's lower than every point here. So there's no interval that we can sketch around it that would make this a min or a max. Where's this function increasing? Well, everywhere, right? F of x is greater than 0, or f prime is greater than 0. Whoops. When x is not equal to a, is it decreasing ever? No. All right, but what's happening here at the derivative? Because at this point, it's kind of weird, right? If I sketch this from the left, the graph is starting to flatten out, so you would expect the tangent line to be horizontal because that's how I'd be facing. But look at this next piece here when it connects. This tangent line is going vertical, right? So from the left, this would say that this graph has a tangent line that's horizontal, but from the right, this tangent line would say that it's supposed to be vertical. Well, it can't be both, right? You can't have two tangent lines. You can't look left and you can't look right at the same time unless you're literally like a chameleon or something, and your eyes can just go in opposite directions, which would be kind of weird. But I don't know, maybe some people can do it. All right, but in this scenario, mathematically, this isn't possible. So what that means in terms of an answer then for the derivative, it's not 0 and it can't be undefined, right? It can't be horizontal, it can't be vertical. It literally just does not exist. There's no answer here because these two things don't agree. There is no derivative here. So anytime this happens, the answer actually is D and E in the standpoint, because from the left and right, the tangent lines wouldn't match and equal one single line. Its rate of change wouldn't be equal to one thing. And this actually occurs again if we were to take the same two pieces in terms of decreasing, and I think this was D and D. If I was to put these things together to create a graph, notice again there is no max or min here, so this answer would be neither. I'm never increasing because this graph is always decreasing, so the derivative is always negative when x is not equal to a. And again, the derivative in this standpoint would be does not exist because the tangent lines wouldn't agree. From the left, this would look like it's horizontal, but from the right, it's vertical, and I can't have both. So because they're going to sit there and continue to argue with each other, They essentially defeat each other. There is no answer for this first part. Um, and there's actually there's really four other different combinations, but this really kind of covers all the ones to really help illustrate the point here. And you could kind of guess that, we didn't do C and C, we didn't do B and B. What if we did, B and, so we did B and A. So what if we did like, um, let's see, what is it? I think it's these on their side. So what if we did A and D, and then what if we did C and B, um, and then there's C and B, and then there's A and D. Right? There's a couple different things. They look like shark fins, but we're not going to worry about it too much because they really just continue illustrating the point. And so what I want to do here is go back and look at what's happening in these where the derivative was equal to 0 and the derivative didn't exist, but I still didn't have a max or a min, versus these where that happened and I did still have a max or a min, and see if we can come up with any other uh, condition that we need for a max and a min so we can find them. So the first one is essentially is that the derivative at A either needs to be 0 or the derivative does not exist. And the second condition also has to hold true. Well, in these four examples here that we saw where it was neither, notice that I was never increasing or never decreasing at any single point. And if I'm going to have a max or a min, there has to be a change between the two. Right? And so these examples are showing if there is not a change, then I can't have a max or a min, versus these are showing that if I do have a change, I do have a max or a min. All right, and so notice again for a min that I'm essentially going from decreasing to increasing, which makes sense. You got to go down into the lowest depths and then increase out of it for a min. Or for a max, you have to increase and then decrease. There has to be a change in sign for the derivative for that to happen. And that's our second condition to show that a function has a max or a min. It's that f prime, the derivative, must change from positive to negative or negative to positive. Right? This has to happen. There has to be an increase to a decrease, or a decrease to an increase, for there to be a max or a min. All right, and this condition right here, we're actually going to look at this more in part 3 of the video, and we're really just going to end this video right here at this point. Now, before I define that, I do want to give you two things to talk about, not really talk about, but just to illustrate, and that's these right here. In this example, let's see if that didn't sweep. In this example, these two right here are examples of what's called corners. So it's when your graph creates literally a corner in the graph. So if you notice that it almost looks like a right angle here. Same thing right here. At the briefest of moments, it is a corner, right? It is a right angle. Versus if we have a scenario like this, the graph comes together at a point. I like to call it a butt. And these are called cusps, though, technically. So these are called cusps. So anytime your curve comes together and meets like this, we'll talk about this more when we talk about applications for the second derivative. But I just want to go ahead and give you that terminology. So cusps versus corners, they're just a little bit different, but they help establish the same thing, that this is where the derivative does not exist. Does not exist. All right, so they have specific names because of that. All right, so what we did is we talked about then that just this first condition wasn't enough, right, to find a max or a min. But it does at least give me a starting value, because if I can figure out where these things are occurring, I can use the second step here to actually guarantee if there is a max or a min that exists there. This first condition at least gives me a list. And so any a value that makes your derivative 0 or does not exist has a very, very specific name, and we call that critical numbers.
All right, these are critical because this is where an extreme value could be, right? And that's kind of the key thing here. Critical numbers do not guarantee the existence of an extreme value, but they do give me a possible location because this is where the tangent line is either going to be 0 or it does not exist. We then have to check and see what's happening with the first derivative to guarantee that. And that again is going to be part 3 for this problem, or for this video. All right, and so here's the critical number definition. So a critical number of a function f is any number in the domain. So you have to be able to plug it in to begin with, such that it either zeroes out the derivative or it makes the derivative not exist. We're going to see a lot of practice with these when we get into part 3 and we put all of this together for the applications of the first derivative. But for part 2, that is it. If you have any questions, let me know. I will post part 3 on Monday. So that'll be what you can see because that's where a lot of the work is going to come from. I will still post some practice for part 1 and part 2. So given a function, tell me where I'm increasing and decreasing, and then telling me where are the critical numbers. So maybe like 6 to 8 questions specifically for that. Otherwise, I'll see you when I see you, which hopefully won't be too long.